So let us do some more problems today before we complete this chapter on group presentations. Our attempt today is to find a standard procedure, a standard way of creating group presentations for abelian and non-abelian finite groups with two generators. So our generating set is actually going to be A is equal to A comma B. Then our aim is to find a standard procedure to create a presentation for a finite group, meaning here it's going to be AB. Then if you want to make the group a finite, the exponent, we should find some kind of m is equal to 1 and n is equal to 1. If this is true, then only it will become a finite. It will become a finite group. But still, this is going to be an infinite group if you don't create a relation between A and B. See, if you have a presentation like this, you can have, let us say, m is equal to 2, n is equal to 3, then you can have AB, A square B, A square B square, then A square B A, then A square B A square. These are all coming from the free group generated by FA. So this is going to be an infinite set if you don't have a relation between A and B. So the idea is to create a relation between A and B in this form. I'll tell you why we are doing this. A to the power of R B for some integer R, some positive integer R, or greater than 0. The reason is that if you have an element like this, then we want to reduce that element to A to the power of something like I times B to the power of J. The basic idea is to list the members or the elements of the group in the form A to the power of I, B to the power of J, where A to the power of M is equal to 1 and B to the power of N is equal to 1. Then only you will be able to limit the number of elements in the group. We are looking for a group of finite order, finite groups. See, if you just say BA is equal to AB, that is fine. But if you tell BA is equal to, if you mention BA is equal to AB, then it automatically becomes an abelian group. So we are actually losing that non-abelian groups when you define like this. See, so idea is like this. So finally, when you generate the group, it will be in this form. with a condition here. And that condition is this. And the reason for that condition is, see, if you want to have elements in the group in this form only, then we should be able to define a binary operation to confirm this format, meaning a to the power of s times b to the power of t. This is one element, and if you multiply this one, a to the power of u, b to the power of v, you should get a to the power of x times b to the power of y. So because if you keep on concatenating these two as in a free group, then it will be an infinite one. So we want to limit, and that is why we are coming a relation like this. It could be like this also, then it will be an abelian group. See, if you do like this, what happens here? A to the power of s, meaning a concatenated s times, then b t times, then we have a u times, then we have b v times. So what we are doing here is we are combining these two, ba to a to the power of r. So this will be a to the power of r times b. Then what we have here, you will have b t minus 1, and here a u minus 1. So you have again another ba here. So if you continue like this process, the multiplication of this group will be defined like this: a to the power of s times b to the power of t times a to the power of u times b to the power of v is equal to a to the power of s plus u times r to the power of t. This r is this r. Okay? Times b to the power of v plus t. If you define the group operation on this set, and with this condition, there is a chance that we can make this as a group. There is a, you see, for all r, it won't be true. So we are trying to find out a condition on r such that this could be a group with elements arranged a as a first component and b as second component, like this: a to the power of I and b to the power of. So that is the idea behind this binary operation, and our claim is this will become a group if r to the power of n is congruent to 1 mod m. If this is true, then only S will become a group. So we are deriving a finite group of order Mn, because if a to the power of m is equal to 1 and b to the power of n is equal to 1, then we'll have Mn elements here. So S will become a group of order Mn. and that could be abelian or non-abelian. If BA is equal to AB, then it is an abelian, otherwise it will be a non-abelian group. And that is a result what we are going to prove first. Then using that result, we will do a couple of problems. Now let us state the theorem, actually result. So let S is equal to a to the power of I, b to the power of j, where 0 less than or equal to I less than m, 0 less than or equal to j less than n, m and n belongs to m comma n belongs to z, positive integers. And let r is a positive integer. So this contains only elements of this form. So define a binary operation on S by a to the power of S times b to the power of t times a to the power of u times b to the power of v is equal to a to the power of x times b to the power of y, which is the same form where we are going to define what is x and y, where x is congruent to s plus u r to the power of t mod m, and y is congruent to t plus v mod m. And that is a binary operation. Still we are not sure S is a group, so that is a condition we are going to enforce here. Then S is a group if and only if r to the power of n is congruent to 1 mod n. And the presentation a comma b such that a to the power of m is equal to 1, b to the power of n is equal to 1, and BA is equal to a to the power of RB gives a group of order Mn. Okay? So, if you want to prove S is a group, then we have to find the identity inverse, and in this case we need to show that the associativity is also true when r to the power of n is congruent to 1 mod n. If this is not true, the associative property is going to fail. So we need to prove 3 things. The first one is A0 B0 is the identity of S, because a to the power of s times b to the power of t times a0 times b0, with the definition it is going to be a to the power of s plus 0 times b to the power of t plus 0, and that is equal to a to the power of s b to the power of t. So this is true for all s and t. That means this is identity. And the inverse of a to the power of s times b to the power of t is a to the power of a to the power of u times b to the power of v, such that s plus u r to the power of t is equal to 0 and t plus v is equal to 0. And that implies v is equal to minus t, and u is such that u r to power of t is equal to minus s. This is actually mod m, and here this is going to be mod n. So we have inverse of every element. To prove the associativity, we will take three elements. So a to the power of s, b to the power of t, a to the power of u times b to the power of v times a to the power of w times b to the power of z, and that is equal to a to the power of s times b to the power of t. This is a to the power of u plus w times r to the power of v times b to the power of v plus z, and that is equal to a to the power of s plus u plus w r to the power of v times r to the power of t times b to the power of t plus u plus t plus u, v plus z, and that is equation number 1. Here this is going to be mod m and this is going to be mod n. So we will associate it in a different way. As times b to the power of t, au times b to the power of v times a to the power of w times b to the power of z is equal to, this is actually a to the power of s plus u rt times b to the power of u plus t, sorry, v plus t, or t plus v times a to the power of w times b to the power of z. And this is equal to a to the power of s plus u rt plus w times r to the power of, well, before we go here, what we need to do is we need to reduce this. This could be more than n. So let us assume that t plus v is equal to nq1 plus r1. This n could be either 0 or 1 because t and v are in the range of 0 and n. 0 and n. So if you add, either it will be less than n or greater than 2n, or it could be less than 2n always, and that's why it could be either 0 or 1. Okay, so this is actually mod n. So b to the power of t plus v will become b to the power of r1 whenever it is necessary. So this is going to be a to the power of S plus URT plus W times R to the power of R1 times B to the power of T plus V plus Z, and that is number 2. So the power of B is same. So this is going to be, the associativity is going to be true if S plus URT plus W of R to the power of T plus V is congruent to S plus URT plus W R to the power of R1 mod M. So we can take out these two straight away. So that implies W R to the power of T plus V is congruent to W R to the power of R1 mod M. This is true for all W. Where is W coming from? W is coming from here, this range, because that's the power of A. And T plus W, T plus V also coming from T, this is coming from N, this range. So this is actually coming from, W is coming from here and T plus W is coming from here. But this is true for all. So we'll take, let W is equal to 1 and T plus V is equal to N. That is possible because it is true for all W, and that implies R to the power of N is congruent to, when T plus V is equal to N, when this is equal to N, this is going to be when T plus V is equal to N, R1 is going to be 0. So R1 is going to be 0 means this is actually congruent to mod M. So the associativity is also true when this condition is true. R to the power of N is congruent to 1 mod M. When associativity is true, this is true. When this is true, then if you go reverse, you will find that this associative property is true. So it is actually if and only if condition. So this part is done. This part is done. And if you look at the presentation here, this is actually a reworded version of the same set here. A to the power of M is equal to 1, and that means the power of M cannot, power of A cannot go beyond N, and that's exactly what this says. So these two conditions are this. And this condition is coming out of our binary operation. What is the binary operation? This binary operation. Okay, so the presentation AB colon A to the power of M is equal to 1, B to the power of N is equal to 1, BA is equal to A to the power of RB comes directly from the definition of S and its binary operation. So that is a proof of this result. We are going to do some problems using this result. So let us do a problem using this result. The presentation A comma B such that A cube is equal to 1 comma B square is equal to 1 comma BA is equal to A square B gives a group of order 6. Gives a non-abelian group of order 6 and hence is isomorphic to S6. So S3. So we are trying to find out a presentation of a non-abelian group of order 6, right? So let G be a non-abelian group of order 6. Then this implies by Sino's theorem there exists a normal subgroup of order 3. Let us say H. See, what it says is p to the power of r times m. If the order of a group is p to the power of r times m, where m does not divide p, where p is a prime, then there exists a normal subgroup of every order of pi. Okay, so here it is p is equal to 3, m is equal to 2, and r is equal to 1. So there exists a normal subgroup H of order 3. Because it's an order 3, H is cyclic. Because it's a prime order. That implies H is cyclic, and let H is equal to so G over H is 2 implies G over H is isomorphic to Z2. And that implies if B belongs to G minus H, meaning it is outside H, then B square belongs to H, because the order of G over H is 2. So B square is equal to H. That implies B square is equal to 1, because otherwise the order of B would be 6. Because B is in H and H has got only 3, the order of H is 3, so B square cannot be anything other than 1. If it is other than 1, then G will be cyclic. So that's what I'm saying, because otherwise the order of B would be 6 and hence G would be cyclic. And which is not the case because G is a non-abelian group. So this implies B inverse is equal to H because H is normal and A is in H. So this implies B inverse belongs to H. And what is H? H is cyclic generated by this, and that implies B inverse is equal to A to the power of R for some R. Actually that should be a 1 less than or equal to R less than or equal to 2. Because this is coming from a group of order 6, so order 3. So it has to be either 0, 1, 0, it cannot be 0. Because if it is 0, then it's an identity of G that cannot generate H. So it has to be 1 or less than 2, less than or equal to 2. But if R is equal to 1, and that implies B inverse is equal to A, and that implies BA is equal to AB, which implies G is abelian. Okay, so that means R should be 2, and that implies B inverse is equal to A square, and that implies BA is equal to A square B. Of course, A cube is equal to 1 and B A square equal to, because this is coming from H, this is coming from outside H, and B square is equal to 1. See, B square is equal to 1. So this is the presentation. B square BA is equal to A square B gives a presentation of any non-abelian group of order 6. Any non-abelian order of 6. And S3 is a non-abelian group of order 6, and that implies A cube equal to 1 or this should be written as actually A comma B colon, and this is comma. That is how it should be written. So A comma B colon A cube is equal to 1, B square is equal to 1, BA is equal to A square B gives a presentation for So let us do one more problem before we complete this chapter on group presentations. So the last problem we are going to do in this chapter is show that there exists no non-abelian group of order 15. What we are going to do is we are going to find out there exists no presentation for a non-abelian group of order 15. So let G be a group of order 15, and that is equal to 5 times 3, and that implies by Sylow's theorem there exists a normal subgroup H of order 5, and that implies H is cyclic, and that implies H is equal to A for some in so let B belongs to G minus H. We are going to follow the same logic as before, and this implies B cube belongs to H, and that implies B cube has to be 1. Otherwise, G will be a cyclic group, and that is not what we want. We are trying to prove that there is a non-abelian group, not try to prove that, try to find out there is a non-abelian group. So because H is a normal subgroup, B inverse is equal to H, and that implies B inverse belongs to H, and that implies B inverse is equal to A to the power of R, because H is cyclic for some R. Actually that R actually is coming from here, so it has to be 1 less than or equal to R less than or equal to 4, right? So for the presentation A comma B, A to the power of 5 is equal to 1, B to the power of equal to 1, BA is equal to A to the power of RB, gives a group only when R mod R is congruent to 1 mod 5. R to the power of cube, R cube mod 1 is R cube is congruent to 1 mod 5. And the values of R are 1, 2, 3 and 4. So the only value of R that satisfies R cube congruent to 1 mod 5 is 1. So if it's 2, then 2 cube is 8, that is not equal to 1. 3 cube is 27, that is not equal to 1. 4 cube is 64, Now 4 cube is 64, and that's also not equal to 1. Mod 5. So the only value is 1, and that implies the presentation, the only presentation for this group with the 2 generators is A comma B, such that a to the power of 5 is equal to 1, b cube is equal to 1, ba is equal to a to the power of r, which is a, b, and that implies G is abelian, and that implies there exists no non-abelian group of order